Chapter 2 Semiconductors. In this chapter, there are many sessions. There are 14 sessions. 2.1 Conductors, 2.2 Semiconductors, 2.3 Silicon Crystals, 2.4 Intrinsic Semiconductors, and 2.5 Two Types of Flow, 2.6 Doping a Semiconductor, 2.7 Two types of extrinsic semiconductors. And then we have the unbiased diode. For bias, 2.10, that's reverse bias. 2.11, breakdown. 2.12, energy levels. 2.13, barrier potential and temperature. And the last session, 2.14, reverse bias diode. There are many sessions that we're going to spend more time to cover in later sessions or chapters. So we don't have to spend lots of time on them in this chapter. The important sessions for these chapters are 2.1 through 2.5. 2.6, we're going to briefly cover that, but it's not that important. We briefly cover 2.7, 2.8, and we can cover 2.8 through 2.13 or even 14 in later chapters. Without further ado, let's start. 2.1 Conductors. Conductors are material that can conduct electrons. Therefore, current, where current just the flow of electrons. And this depends on the structure of the element. Of course, depends on the type of elements. Not all elements are conductors. There are also insulators and, for this course, semiconductors. Let's begin with the valence orbit. That's the most important thing that can use to distinguish the three categories of materials. To emphasize the importance of the valence orbit, we define the core of an atom as the nucleus and all the inner orbits. Let's take a look at this figure. Here is a Bohr model of the copper element. Copper has 29 protons, so the big circle in the center with the plus 29 represents that. This is the nucleus. And let's don't worry about the neutrons. Neutron doesn't play an important role here. As you can see, there are 29 protons for the copper atom. Since this is an atom, the number of electrons need to be same as the number of protons. There must be 29 electrons surrounding the nucleus. They are distributed and floating around it in those orbits or shells. The green circles here represent those electrons. A formula that can help us to know the maximum number allowed electrons per shell is this formula. N equals to 2n squared. The uppercase N means the maximum allowed electrons for a shell, and the lowercase n means the shell number or the orbit number, the nth orbit. With that formula, and we take a look at this figure again, we know the meaning of those electrons for a shell. The shell that's closest to the nucleus is shell 1. And that shell, that circle, has only 2 electrons. Because using the formula, 2 times shell 1, which is 1, 2 times 1 squared equals to 2. Shell 1 can contain no more than 2 electrons. And then shell 2 use the formula 2 times 2 squared, which is 8. So shell 2 contains maximum of 8 electrons. Using the formula, the third shell contains 18 electrons. If we add 2 electrons on shell 1 and then to 8 on shell 2 and 18 on shell 3, we have 28 electrons. However, for copper element, there are 29 electrons. There's one more electrons, so we have to place the electrons on one more shell. That is the shell 4, or fourth orbit. So we put that on this shell. This is the outmost shell, and is the most important shell in terms of knowing the characteristics of an element. So we give that a special name. We call it valence shell. For electron or electrons on this valence shell called valence electrons. We know the outmost shell and its electrons are the one playing the most important role. So usually we don't need to worry too much about those electrons within that outmost shell. In other words, we can remove them. After removing all the inner electrons and the shells, we can see that this diagram has only one electron for copper, and this is the valence electron. Of course, other elements may have different number of valence electrons. And that's the active electrons, corresponding to one active proton. So the nucleus will put a +1. This is called the core diagram of copper.